Hey guys, let's talk real quick about spectral lines and how they're produced, because that's pretty much what the first lab this week is about, and it's a major part of what we do when we look at stars in astronomy. So what happens is we'll consider hydrogen. We'll do that one. Why? Because it's easy. Hydrogen just has its element number 1, and it just has 1 proton. And when you go over the section on atomic structure, remember protons and neutrons are in the center of the atom in the nucleus, and then the electrons are spinning around outside. Hydrogen is crazy simple because hydrogen has 1 proton in the middle and 1 electron going around it, and that's it. So if we can try to understand hydrogen, then the same principle applies to everything else. It's just a lot more complicated. All right, so I just have drawn over here just a real simple model of hydrogen. So the red thing in the middle, there's the proton, and then you just have a little electron in an orbit. Okay, simple, right? Here's what happens. And again, nobody knew this like 100 years ago. We had to figure this stuff out based on strange results we got through experiments. So here are the things we figured out. And one of the theories for how atoms behave is called quantum mechanics. So all of these results are from quantum mechanics. You want to learn about quantum mechanics, you should probably change your major, and you could take semester after semester learning about quantum mechanics, how the subatomic world behaves. But we won't do that. I'll just tell you the results. So here are the results. The orbit, ordinary hydrogen, when the electron is spinning around the nucleus, just ordinary hydrogen left to itself, the electron spins around in an orbit that is called n equals 1. And here's what that means. It's possible for the electron to spin around the center, spin around the proton in another orbit. Sort of like, and don't take this too seriously, but sort of like planets going around the sun, right? Mercury has an orbit, Venus has an orbit a little bit further out, and then the Earth, and so on. And so electrons can orbit at different distances. The difference is that they can only orbit at certain distances. You could imagine a planet having any orbit around the sun, any distance from the sun. It's allowed, it's fine. There just happen to be planets in specific locations. But there's nothing preventing a planet from forming 4.7 AU away from the sun, or whatever. You could make up any number you want. Everything is fine. For atoms, though, it doesn't work like that. For atoms, electrons can only be in very specific orbits, and they're labeled as 1. And let's see if I can draw it. And then there is orbit 2. That's not exactly centered, right? No, it'll be okay. And then there's going to be an orbit 3. And then there's going to be an orbit 4. Oh, I'm going to have to be really careful. And then there's going to be an orbit 5. I think there's better drawings of this in the book. They're supposed to all be centered, right? But I'm not that good. Okay, so there's 1, and then we just start counting out from there. It's really easy. So this would be 2, oops. This would be 2, 3, 4, and 5, just counting out. Those are the allowed places where the electron can orbit. They're not equally spaced. The jump from 1 to 2 is the biggest jump, and then the jumps are supposed to get smaller as you go out. It's not obvious by looking at my drawing, but that's the way it's supposed to be. Okay, here's what happens. If an electron is sitting there at 1, it's possible. How do you kick it up to 2? What you have to do is you have to give the electron some energy. There's a couple of different ways that could happen. Electrons can soak up energy by absorbing light. It turns out that electrons are what are responsible. I better write this down because I'll probably keep saying it. Electrons are what are responsible for emitting light. let me say it like this. Electrons emit and absorb light. That's neat. So if an electron absorbs a certain amount of light, it can jump up to level 2, because jumping up a level means it needs to gain energy, right? When it falls down, it loses energy. That kind of makes sense. So if an electron absorbs light, it can jump up to the next level, or it could jump up from level 1 to level 3, or to 4, or to 5, or whatever. We won't worry about that right now. Let's assume that this electron is going to get up to the next level by another method, another way an electron, in fact, the only other way we're going to talk about, that an electron can be kicked up to another level by absorbing energy, is a collision with another hydrogen atom. Electrons can sort of act like little shock absorbers. So if one hydrogen atom collides with another one, bang, what happens is that the electrons can jump up. They can absorb some of that energy and they can jump up. Okay, well, what happens if an electron jumps up to 2? Boop. What happens is that it stays there for a little while, but then it's unstable, they always fall back down again. They always want to get back to level 1, and they can stay on level 1 as long as they want. So it can jump up to 2. So 1 to 2 by absorbing energy. And right now we're just going to say that that's from a collision with another hydrogen atom. So the electron can jump up to 2, and then what happens is that it always falls back to 1. But here's the idea. When the electron falls back down, it loses energy, right? How does it lose energy? It radiates. It emits a little flash of light. So when it goes down from 2 to 1, here comes a little flash of light. Neat. So that's how light is emitted from these atoms. Electrons are kicked up to higher energy levels, and then when they fall back down, when they cascade back down, each jump down emits a little flash of light. What happens if an electron gets kicked from, let's say, 1 up to 3? So there's an electron up here at 3. Now what happens? Well, it stays there for a little while, and then it's going to fall back down again. It could fall from 3 down to 1. That's possible. It's also possible that it could fall from 3 to 2 and then from 2 to 1. How does it know what it's going to do? It turns out it's completely random. It's a roll of the dice. It's slightly more likely to fall to 2 and then to 1 than to fall from 3 to 1. How much more likely it is governed by quantum mechanics. We can calculate it. But anyway, it's totally random. 80% chance it's going to go 3 to 2, 20% chance to go from 2 to 1. I'm making it up. I don't know. It's something like that. Okay, so let's say it falls from 3 to 2. So when it falls from 3 to 2, it emits a little flash of light. Now, it turns out, I have to use that phrase, it turns out that that little flash of light, when it falls from 3 to 2, happens to be right in the visible band. In fact, that's got a particular color, 656 nanometers. Remember, all the colors from 400 to 700 nanometers, you can divide those up and you can give each specific little band its own particular color. 656 nanometers is its own little particular color of red. This has a nickname. This is the transition from 3 to 2. This is 656 nanometers, and this is called H alpha. And sometimes you'll see it written like that, H with a little Greek letter alpha after it. It's just a nickname because a long time ago they didn't know what was causing it, and they knew it was coming from hydrogen, and it's the brightest line coming from hydrogen, so they just called it H alpha. Okay. That's from 3 to 2. And then when it falls from 2 to 1, now what do you notice? From 2 to 1, as it falls from here back down to 1, and I sort of drew it that way on purpose. Notice that 2 to 1 is a lot bigger jump than 3 to 2, right? That means when it goes from 2 to 1, it loses more energy than 3 to 2. So it's going to emit that flash of light from 2 to 1 is actually higher energy light. And it turns out it's actually in the UV. This is 121, I think that's right. 121 nanometers is the 2 to 1 transition. That's in the ultraviolet, right? Because you have to be 400 nanometers before we can see it as just regular violet. So 2 to 1 is invisible to our eyes. It emits an ultraviolet flash of light. Okay, so 3 to 2 gives us this red light. You could, with a stronger collision, you could kick the electron up to, let's suppose it was, you kick it up to 2, and we just had it kicked up to 3. Suppose we kick it up to 4. So an electron that starts at 4, there's lots of things that it could do. It could fall to 3, and then down to 2, and then to 1, or it can go from 4 to 2 to 1, or 4 to 3 to 1, right? There's all these different, they're called branching ratios. There's all these different possibilities now. It starts to get complicated. But one thing that it could do is it could fall from 4 to 2. If it falls from 4 to 2, look at that. That's a little bit bigger jump than 3 to 2. So that flash of light is going to be a little bit more energy. And it turns out the little bit more energy than red, this turns out to be sort of a blue line. This turns out to be 486 nanometers. All right. So the transition of an electron from 4 to 2, levels 4 to 2, gets you 486 nanometers. The nickname for this one is, guess what, H beta, alpha and beta, and sometimes you'll just see it written like that, an H with a beta after it. Okay, so that's the pattern. If the jump down is farther, you get a higher energy light from it, higher energy flash. Okay, so the last one that we'll do is, suppose the electron jumps from 5 to 2. You can kick it all the way up to 5, and then it's possible it could fall down to 2. That's even a little bit more higher energy light, right? And this one is roughly violet. Hope that shows up. The violet light is more energetic, and this one is 434 nanometers. So 5 to 2 is another flash of light that's 434 nanometers. Alpha beta, this one must be called H gamma. And it looks something like that. Okay, so here's the deal. Whenever you have a bunch of hydrogen, let's say I've got hydrogen gas, and I heat it up. Either it's hot hydrogen gas outside of a star, or in the case of the lab, maybe it's in a tube and I pass electricity through it that heats the gas up. So what happens when the gas is heated up, that means the atoms are moving around faster and faster, and they're slamming into each other, right? Lots of collisions. And so lots of electrons are being kicked up to these higher levels. And then they start cascading back down again. Each time they go back down, they give off a little flash. So what happens is that hydrogen gas shines in these particular colors. It doesn't shine with all colors. Hydrogen can't emit all colors. It can only emit the colors corresponding to these jumps. So if I heat up hydrogen gas and I split the light apart with a prism or a diffraction grating, what I'm going to see is not all colors. I'm just going to see these particular colors. I'm only going to see these 3. It turns out there's another one from 6 to 2 that's even more violet, but this is good enough. So when I look at hydrogen through something that produces a spectrum, I just see 3 bright lines. I don't see all the colors, which is exactly what we see in the lab. If you go look at hydrogen in the lab, what you'll see is running from 400 nanometers to 700 nanometers. What you're going to see is you're going to see a violet line, and then you're going to see at about 434, and then at 486 you're going to see a whatever the heck that is, bluish green line, H beta. And then over here at 656 you're going to see a red line. And here's the coolest thing, is that we discovered that all elements have their own unique barcode. This really is a barcode. This is the hydrogen spectrum. And it turns out every element has its own spectrum, its own barcode. It's like a fingerprint. This is amazing because this means that when we look at a star and we see a particular set of lines, in this lab you're going to go through and see the different spectra made by mercury and neon and sodium and so on. Each one has its own little fingerprint, its own little barcode. Then we know what elements are present, right? This is called spectroscopy. So we just look at the light that a star emits, and that light, if we look at it carefully, pass it through a diffraction grating, smear the light out, and look at it, what we're going to see is what's revealed is what the star is made of. The thing that emitted the light, we can tell what elements are present. Very, very cool. This happens to be the hydrogen spectrum, and it's pretty simple. Each element has its own unique barcode, and they're all different. Helium spectrum is a little bit different. I think in the helium spectrum, it's kind of the same. 400 to 700. If it's helium, I think there's a red line, and then there's another line here, and I think there's like even a bluish line here. The thing that helium has, what you're going to find out, what you're going to see, helium also happens to have a yellow spectral line. Because its structure is different. It's got 2 protons, it's got 2 electrons. Everything is way more complicated for helium and then going up the table. But the upshot is that it's got its own barcode. So if we see this particular set of lines coming from a star, we know there's helium there. Very, very cool. So this is where, basically, this is where light comes from. This is how stars emit light, and this is what we look at when we look at stars. So the first lab this week is going to be you getting just a little bit of practice and actually seeing these generated in real time. Well, if you were on campus, you would actually take the little thing and you would actually look at the gas and you would actually see these things. So now you have to look at me doing it, taking pictures of it. But anyway, these are real spectra generated by the tubes. So next time is we'll look at some other tricks that light can do.